Hello, and welcome to this problem-solving video on interference conditions. In this video, we're not actually going to be solving a problem fully. Instead, we're going to be looking at the general approach to solving problems where you have two waves which are arriving at some point together, and you want to be able to say something about whether you're getting perfect constructive or perfectly destructive interference at that point where they arrive. So that is the general question. What's happening when we're adding two waves? So let's pick a setup. We're going to have sort of two speakers, say, or whatever kind of source of our wave. It's emitting those waves, and they're moving along, both going to arrive at some point over here. And what we want to say, or what we want to know, is what are we seeing at that point? So you can see that these waves are arriving in phase. I'm adding a crest to a crest, and now a trough to a trough. So I can plot as a function of time what the wave superposition looks like at this point, and that's what's going on down here. And you can see when you add the crest to crest, you get a really big crest. The trough to trough gives me a really deep trough in my superposition. So let's think about what's going on there. So the result that we were plotting down at the bottom depends on the relative phase of those waves. In order to describe what was happening, I had to tell you that we were adding crest to crest and trough to trough. So that meant that those waves were in phase, as I said. But what if they're not? So if they're not in phase, we know that we're going to get interesting results. So in particular, if there's a change between the two, if there's a relative phase difference of any multiple of 2 pi, then that really means that they're still in phase. Right? Because if I shift 1 by 2 pi, I've just shifted it a whole wavelength, which means I've jumped from one particular crest to the next one over. I haven't really done anything. So that's a shift of 2 pi, or 0, or 4 pi. Then I'm shifting, if I'm talking about 4 pi, I'm shifting now 2 wavelengths. 6 pi would be 3 wavelengths, and so on. So those are really just the same as the picture we plotted. It's indistinguishable, except that the one wave presumably would have been further ahead, potentially, depending on exactly how I introduced that phase difference. So, okay, if this is the case of their relative phases, then I will have perfectly constructive interference. On the other hand, I know that if I'm adding a crest to a trough, then I will get perfectly destructive interference. And that, of course, corresponds to shifting it not by factors of 2 pi, but rather by odd multiples of pi. If I shift it by pi, or 3 pi, or 5 pi, then I'm always shifting it by a whole wavelength plus a half of a wavelength, and that shift of a half wavelength is exactly the thing that's getting me to be adding a crest to a trough. So if I've got 2m plus 1 times pi, then I'm getting perfectly destructive when that is the difference in my phases. So how do we actually change the phase of one wave compared to the other? Well, one obvious way is to directly change the phase of one of these waves. So if I start playing around with the phase that I am emitting at, so my phi naught, my phase constant for this second wave, then I know that, assuming I've kept all the wavelengths and everything else the same, then my entire phase difference is just due to the difference in those initial phase constants. So that one over there has a phase constant, say, of 0, and that one I'm shifting, and you can see that it is changing exactly what's happening. If I shift the phase constant by a factor of pi, well, that's when I get perfect destructive interference, and then there it is, perfect destructive, and then I can get, again, back to constructive interference by restoring to any multiple of 2 pi. And so that's all that's going on there. I keep changing the phase of this one. It keeps changing what my superposition is doing. So certainly I can change that initial phase constant. Now I can also change the distance that one of these waves has to travel, or really both, by shifting the point at which I'm looking. As I do that, of course, the red one is traveling a shorter distance and the blue one is traveling a longer distance. So if I work out what that distance is, this extra distance d that, say, the blue one travels compared to the red one, well, if I know that extra distance d, then I can ask myself, what phase difference does it introduce? It introduces this phase difference here. d as a fraction of wavelength basically is the important part of that expression. It just says, well, if I shift the distance by half a wavelength, so that it's the relative distance again, d is the difference between the distance that the red and the blue travel. If that is of half a wavelength, or 3/2 of a wavelength, or something that is some odd multiple of half a wavelength, then I'm exactly in this case where I'm going to be adding a peak of one wave to the trough of the next one, if I've shifted it by half a wavelength. And so you can see that happening here as I change this point right about here, where that superposition went flat, so right about here, I am now at a difference of 1/2 wavelength in their travel distances to that particular point, and so I do indeed get perfect destructive interference. And all we're doing with this 2 pi in this expression is just relating that back to angles instead of fractions of wavelength. So then I can ask myself, as I shift d, changing the relative path difference, if that works out to be an even multiple of pi, this whole thing, then I know that I'm looking at even multiples, which was my condition for perfectly constructive interference. And if I'm getting odd multiples, then I know that I'm actually dealing with half wavelengths, odd multiples of half wavelength. That's how I get odd multiples of pi here, and that's giving me exactly the condition we wrote down for perfectly destructive interference. Now there's other ways of changing this too. I can of course delay the start of one of the waves, or I can even change the location of one of the waves, and we can derive similar sorts of expressions. I leave that to you as food for thought.